So a few months back, I finally got talked into trying out some short-form content, and after we did a bunch, folks started asking if we could make a compilation of them to watch on YouTube or over on Nebula and our audio-only podcasting platforms. I figured we would release them in groups of 20, so unlike the solo shorts, you might want a drink and a snack. I'll talk more about it at the end, but by popular demand, and without further ado, here's the first 20 shorts we produced in summer of 2023. Quasar Cannon. A quasar is a quasi-stellar object many times brighter than an entire galaxy, often radiating more power than a quadrillion normal stars, and releasing a billion times more power every second than a megaton thermonuclear bomb. Quasars are less common nowadays, as we believe they were caused by large quantities of matter falling into supermassive black holes in a core of a younger and more turbulent galaxy. It should be possible to set off such an event artificially, or even use a smaller black hole to generate the effect, such as we believe causes gamma ray bursts. Much as we can convert an entire star into a giant death ray, as with the Nyko-Dyson beam, it should be possible to create a quasar cannon around a black hole that had a more focused and targetable gamma ray beam, potentially millions to trillions of times more destructive than even a Nyko-Dyson beam. For more examples of such megastructures, like the Quasar Drive, see our episode The Megastructural Compendium. Birch planets. I sometimes get asked what the biggest artificial planet or habitat you could possibly engineer is, and an answer comes from the late great Paul Birch, who suggested you could build an enormous planetary shell around the supermassive black hole at the center of our galaxy, 4 million times as massive as our own sun, or 1.4 trillion times the living area of Earth. More living area than if every rocky planet in this galaxy was terraformed. And yet this is just the bottom end of the megastructure we name in his honor, because you could feed all your surplus matter in a galaxy into a black hole, using that to power your civilization, and build a structure around it with normal Earth gravity that was nearly a light year across, massed as much as our entire galaxy, and had a billion times the living area of Earth, and likely more than every habitable planet in the observable universe combined. See our episode Mega Earths for details on how such titanic creations can be made under known science. Aliens beyond the galactic rim. About 5 years back, there were studies showing how rare phosphorus is in the cosmos, and of the 6 key elements making up 1% or more of you or I or other organisms on this planet, it is the only one found in tiny quantities and appeared as a possible bottleneck on what planets might harbor life, a possible filter for the Fermi paradox. We also believe that many regions of the galaxy might be low in phosphorus and potentially devoid of life, especially orbital regions like the galactic rim, and that life would not plausibly occur at more than twice the distance Earth is from the galactic core. But an article in Science News earlier this week reports a team of astronomers from Arizona having detected relatively large amounts of phosphorus in a vast gas cloud 3 times as far from the core as we are. I'll link that article in the description, and you can also check out our episode, Fermi Paradox, the Phosphorus Problem, for more details, but it highlights that seeming paradox. In a universe so huge, ancient, and seemingly friendly for life, where is it all? BWC Megastructure. BWC, or Because We Can Megastructures, is a nickname for those types of hypothetical megastructures which are interesting as concepts but wildly impractical enough that we would only expect them to be built for prestige or tourist value. Though in a system of potentially millions of more normal habitats and worlds, such rare oddities might be built economically for their novelty value. Examples include donut planets, chain worlds, sombrero planets, cube-shaped planets, or flat Earths. It should be noted that sometimes a BWC can have specialized values, as for instance, a coin-shaped world allows identical seasons, temperature, and weather at all points, ideal for a beach resort planet, something a classic spherical planet lacks, with frozen wastes at the poles. What qualifies as a BWC megastructure is somewhat subjective. For more examples of these types of megastructures, along with more practical designs, see our episode The Megastructural Compendium. A hegemonizing swarm is a living weapon or self-replicating machine which seeks to turn every last available bit of matter into more of itself or a desired construct. Examples can include Grey Goo, a paperclip maximizer, the Borg from Star Trek, the replicators from Stargate SG-1, or arguably even regular biological life itself. A hegemonizing swarm might also be a runaway terraforming device, trying to turn all the matter in the galaxy into space habitats, artificial planets, computronium, or giant weapon and defense installations. Whatever its end goal, it is a relentless swath of destruction, like some killing cloud, descending on a world to disassemble everything and destroy all there was. A hegemonizing swarm is usually assumed to be apocalyptic, and if it has any personality at all, to be callous, stupid, unwavering, or unwilling to show mercy or negotiate. However, as we explored in our episode The Paperclip Maximizer, they may develop novel variations of their goals or personality. A solar moth is a very simple design with few failure modes, and a solar moth might use very nearly anything that can be vaporized as a propellant, including common elements in deep space like hydrogen, water, methane, or ammonia, making them a potentially good engine for probes and long-term monitors in the asteroid belt or Kuiper belt. Scaled up, a solar moth is a good way to move a comet, simply using it as propellant, as energy beamed to it from in-system will create far less outward thrust than the energy received being used to vaporize ice and shove inward toward the solar system's inner regions. Solar sails operate on the principle that photons of light carry momentum which may be absorbed by opaque objects, transferring that momentum, or reflected by reflective objects or mirrors, which can double the imparted momentum, sending the photon back with the same but opposite momentum, or deflecting at an angle to send both sail and deflected photon off in different directions. This allows a sail to quarter sunlight. A fusion candle is a type of hypothetical megastructure that is an enormous fusion drive that is placed in orbit of a gas giant, like Jupiter. The fusion candle is designed to suck hydrogen, deuterium, or even helium out of the atmosphere, run it through a fusion reaction, and use the energy released to send out two superheated rocket jets in opposite directions, up and down. The lower levitates the platform, while the higher goes into space to shove the planet in a desired direction. By this method, you can move a gas giant to a different location, such as if you wanted to move one closer into a system to warm its moons for terraforming. See our episode Colonizing Jupiter for more discussion, or our Megastructural Compendium for more examples of megastructures like the fusion candle. Non-equatorial space elevators. One of our biggest goals in space development is to make space travel affordable to everyone. That's where devices like orbital rings, tethered rings, space towers, launch loops, and mass drivers come in. And perhaps the best known of these megastructures is the space elevator, an enormously strong tether reaching from some spot on the equator to geostationary orbit or beyond, tens of thousands of miles above Earth. A major hurdle to building these is finding a material strong enough, but the other problem is that the tether must be at the equator to avoid it whipping around, and few major cities are on the equator, but we would like to be able to leave directly from those places. However, we can place multiple tethers, some originating from the south hemisphere, some from the north, to meet high above like guy wires on a tether and hold each other in place, allowing space elevators to be sited wherever we want. See our episode Space Elevators to learn more. Building artificial planets. We often talk about building enormous space habitats for people to live in as alternatives to trying to terraform planets like Mars or Venus to somehow make them livable. And yet, as cool as a big cylinder or ring habitat is, for a lot of folks a planet like Earth is going to be preferable, and you can potentially build a planet just like Earth. Our usual assumption is that you would skip on using rare materials like iron or uranium in the core in favor of very abundant materials like hydrogen or helium, or even dark matter or black holes, and thus be able to build a lot more Earth-sized planets with a lot less rocky matter. And yet, artificial planets identical to Earth isn't your only option. You can build ones very like Earth in climate and gravity, but 100 times larger in surface area, or even millions of times bigger than Earth, as we explored in our episode Mega-Earths, where you might have a planet that is orbited by a star, has a black hole in its center, and has a surface so big that it has entire archipelagos of large continents on it. Computronium is a catch-all term from speculative science and sci-fi for any type of matter which supports computation or thought. While human brains classify as computronium, the intent is usually to describe substances designed to maximize computation, and usually very large objects dedicated to this goal. Earth, for instance, is only 2 parts per quadrillion human brain, so a planet-sized brain would have 500 trillion times the brains of the entire human race combined, and possibly far greater if you had a form of computronium vastly superior to a human neuron. We can contemplate entire planets or star systems turned into vast computers, such as a Jupiter brain or Matryoshka brain, able to tackle impossible mysteries or simulate whole universes and emulate trillions of people living inside them. A post-biological civilization might seek to turn all matter in the universe into computronium, possibly via a hegemonizing swarm. See Matryoshka brains for more details. Deciphering alien codes. As we search for extraterrestrial intelligences out in the cosmos, one common question is if we could even recognize their signal or ever hope to decode their language. Folks often point to tons of untranslated ancient tablets as evidence. If we can't decipher things written by members of our own species, what chance would we have with some aliens from an entirely different evolutionary origin? You might have seen recent articles about AI translating those old tablets with relative ease and speed. At its core, this was never a problem of those languages being alien, merely us having so few examples to work with. Fundamentally, language is about conveying concepts to others, and some will be universal, like math and physics concepts, and can serve as a Rosetta Stone with sufficient examples, which we explored in greater depth in our Alien Languages and Cryptic Aliens episodes. It wouldn't be fast or easy, but if aliens are out there, we should be able to talk to them. Astro Chickens and von Neumann probes. The galaxy is huge. It's so big that if we sent out a new space probe to a star every single day, it would take over 1 billion years before we sent one probe to each star, and that's just in this galaxy. And almost none of those probes would reach their destination, as they might need to keep functioning for tens of thousands, if not millions of years to get to their destination. One answer to that is the von Neumann self-replicating probe, a class of probes that arrives at a nearby star, rendezvous with some asteroid or small moon, and makes several copies of itself to explore that system and send others to every star in range. The Dyson Astro Chicken is a type of von Neumann probe massing 1 kilogram that hatches solar panels as it approaches a star and uses those to run an ion drive and self-replication processes. See our self-replicating spacecraft episode for more details. A popular speculation in sci-fi is that the dinosaurs might have been an advanced civilization and that they were wiped out by some unnatural cataclysm, possibly by a galaxy-wide war among dawn civilizations that left everything in ruins and from which we are just now recovering. And this is a popular solution for the Fermi paradox about where all the aliens are. Good stories, but we have no evidence dinosaurs ever had big brains, though some would argue that we have little evidence about them at all. Even 100 fossils from a 10 million year period is just one fossil per 100,000 years, which wouldn't tell you much about humanity, especially if it was a gorilla or dolphin fossil, and skull size says little of intelligence. Could millions of years erase evidence of prior civilizations on Earth? See our episode The Silurian Hypothesis to see if we could even find such ruins, if they existed, or if we would leave any ourselves. Will humans in space be taller? It's popular in science fiction to suggest people who live on planets with higher gravity than Earth would be shorter or stouter, while those living on low-gravity places like the Moon or Mars, or in the microgravity environment of space itself, might be tall and thin. There is little reason to think people would need to be taller in such an environment, especially as it's easier to climb or jump up to grab something high in low gravity, though many other variables might make extra height a benefit or disadvantage. However, low gravity means less need for thick, dense skeletons, so you might see skinnier people and those with more hand-like feet and skinnier legs. See our episodes Life on a Low-Gravity Planet and Zero-Gravity Civilizations for more discussion of how people and life in general might adapt to these environments. The Stanford Torus is an enormous 10 million ton space station habitat first proposed in 1975 to house 10,000 inhabitants at a station diameter of 1.8 kilometers or just over a mile. The habitat section is a wide, hollow, donut-shaped ring, or torus, whose inner edge is transparent and whose outer edge is for people and their landscape. By rotating once per minute, it provides spin gravity to the inhabitants and visitors, and can use a large mirror to send filtered sunlight into the habitat.
The Stanford Torus has many variations, often including multiple rings of larger diameters for more living area and various ancillary facilities, from power collectors to refineries or smaller agricultural stations. A docking module at the center includes secondary mirrors to direct sunlight from the primary mirror to the habitat, as well as a space for ships to dock and unload, or be repaired or built. For more examples of space habitats, see the Megastructural Compendium. Medical technology has revived people who have stopped breathing or whose heart has stopped, but could it revive those who are already brain dead, and if so, for how long? The answer is likely yes, as we better learn how our brains operate, but this analogy often gets stretched to imply recovery could be done days or even centuries later, that in this way we could resurrect the ancient dead, or that a super-powerful computer mind could, which is the source of the Roko's Basilisk retrocausal thought problem. By back-calculating the trajectory of particles decaying or leaving a brain, we could resurrect that person by rebuilding that brain, especially if well-preserved or frozen. However, even without involving quantum mechanics, many systems would likely be too chaotic and complicated to model even with planet-sized computers, and grow exponentially worse every day that passed without proper preservation efforts. See our episode Technological Resurrection for more discussion of the potential methods and problems. We often hear that our galaxy will collide with the Andromeda Galaxy, our nearest neighbor, and that this will begin happening in a few billion years. But this is not quite a correct way of looking at things. Indeed, one could make a case that Andromeda and the Milky Way are merely part of a larger galaxy and are simply condensing, as they form a roughly dumbbell-shaped collection of stars with dozens of smaller galaxies in and around them, all being drawn together over the last 13 billion years, and finishing over the next several billion. The only other significant galaxy in the region is Triangulum, and it will merge with us at about the same time, leaving a larger galaxy that will eventually be isolated by Hubble expansion from all the other merged galactic islands in the expanding ocean of the night. See our episode Intergalactic Voyages to learn more about this process, intergalactic colonization ahead of Hubble expansion, and larger neighboring galaxies like the Council of Giants. The Bernal Sphere is perhaps the oldest space habitat design, dating to 1929, and is a hollow sphere originally designed to be 10 miles or 16 kilometers in diameter, in which inhabitants would live inside. The original design by Bernal hollows out an asteroid to build a sphere around it, which may be replaced with a wider one as you grow, and considers a hollow transparent outer sphere for sunlight. In this way, asteroid mines in space might slowly turn themselves into larger habitats for bigger populations and more diversified economies. Others, such as Gerard K. O'Neill, would refine the design, as his Island 1 and Island 2 stations, and introduce rotation to give the stations spin gravity inside. The Babylon 5 TV show features a Bernal sphere of this type. For more examples of space habitats, such as O'Neill's Island 3 design, known as the O'Neill Cylinder, see our episode The Megastructural Compendium. Nuclear fuel contains millions of times more energy than chemical fuels rockets use, and seems ideal for faster space travel, but they must transfer that energy to propellants, and the maximum speed of that ship is controlled by that propellant temperature and momentum out of the back. Rocket nozzles and other equipment will begin melting as their temperature rises, so we either must use slow propellant, slow accelerating ion drives, or find a way to move energy from our reactor to that gas propellant better. The light bulb is at 40,000 degrees Fahrenheit, or 22,000 Celsius, where most of its light is ultraviolet and which quartz is transparent to. That ultraviolet can pass outside without warming that chamber as much, strike a propellant particle, and transfer its momentum, which then leaves the rocket at high speeds. This is believed to be a safe and efficient engine design able to achieve 3 to 6 times the speed of our best chemical rockets. See our episode The Nuclear Option for more discussion of nuclear-powered spacecraft. Von Braun Wheel or Station. First designed by Wernher von Braun in 1945, this ring or torus-shaped space station is one of the earliest models of space station that included artificial spin gravity. The original design is made of 20 cylindrical segments, 3 meters or 10 feet in diameter, and 8 meters or 26 feet long, each linked at the end to the next by an airlock door at a slight angle to form a circle of 20 segments and connected by a spoke to the central hub. This is also popularly known as a wheel design, and some inflatable versions are essentially identical to a large bicycle wheel. By having spokes or tethers connected to a hub, it is possible to add segments as you go, rather than waiting for a complete circle. And some suggest that rocket boosters could be collected and repurposed to make such a station instead of letting them drop back into the atmosphere to burn up. See the Megastructural Compendium for more examples of space habitats and stations. So that will wrap us up for our first SFIA Shorts compilation. Given that I do 8 or 10 shorts a month, we'll probably release a new compilation about 5 times a year. And please make sure to hit the like and subscribe buttons, as well as the notification button, if you want alerts when these and other episodes come out, along with our episode polls, so you can vote for what topics we do episodes on, and suggest other episode topics for future polls. For our longtime watchers, the plan is to move away from our monthly live stream to more short-form content and occasional mid-length episodes when a short I'm writing just doesn't fit in the 60-second shell and needs more like 10 or 12 minutes, as happened recently with our unannounced Busord Ramjets episode, and I'm hoping this lets us occasionally cover recent events of note since these days I write our normal weekly episode 3 months ahead of time. We're going on hiatus on the live streams after New Year's Eve 2023-24. YouTube hasn't been promoting them well anymore in favor of shorts, and they are disrupted to family time on Sundays, though I'll probably bring content of that type back down the road. I always like to try new things, like our 3-hour Fermi Paradox Compendium next month, and as we get into the new year, we'll start having content coming over from Nebula monthly and some more bonus episodes made on the fly, along with these compilations, so total content should be on the rise. As always, you can support that future content by donating to our show by PayPal, Snail Mail, Patreon, Subscribestar, or just joining Nebula, our streaming service, if you want to see our regular episodes all early and ad-free, and Nebula originals like this month's Dark Stars at the beginning of time. And until next time, thanks for watching and have a great week.